Hello, dear students. In the last class, we have to discuss some problems of a groups and its properties. Now, today's we start a subgroup. We start with the property definition of a subgroup, and then we have to some examples and some properties of a subgroup. So, subgroup, we simply say that let G be a group with respect to the binary operation star. A subset H of G is called a subgroup of G if H forms a group under the same binary operation. Means we can simply say that simple language, if we have a G is a group and we take H as a subset of this G, and this H itself is a group under the same binary operation as the operation of a G. So we can say that H is a subgroup of a G. We write H is a subgroup of a G in these notations to express that H is a subgroup of a G. Very simple example of subgroup is set of integers is a subgroup of set of integers under addition is a subgroup of a set of real number under addition, and also set of a complex under addition. So, set of integer is a subgroup of a R and C, and similarly R under addition is a subgroup of a C under addition. Now R is also is a subgroup of the complex number under additions. Now we have to try some examples for a finite. Let G is equal to 1 minus 1 I minus I, and we already show that this is a group under the binary operation is multiplication, and consider H is equal to 1 and minus 1. So, H is a subgroup under the multiplication is there. So, simply we can say that if we have to verify this by the using the Cayley tables, we have to take under multiplication 1 minus 1, 1 minus 1. So, 1 minus 1 minus 1, and this is equal to 1. So, you can see this is identity element of this under multiplication is a 1. So, this satisfies this identity elements is hold in this case, and every element is a inverse of itself. Minus 1 is the inverse of a 1 and 1 is a inverse of a 1. So, every element has its inverse, and this is clearly H is a subset of a G, and then we can say that H is a subgroup of a G. So, H itself is the same satisfies the properties of a group under the operation of a multiplications. So, this is a clearly is a subgroup of a G. Observe that every group of G with at least 2 elements will always have at least 2 subgroups. So, we have to just say that, namely if a G has at least 2 elements, so we can say that this always have at least 2 subgroups, namely G itself, and then we have a identity element. So, G itself and the subgroup consisted only the identity element. So, this is H is only the identity element, or H is equal to itself is a G. These are the two trivially these are the 2 subgroups for every group if we have at least 2 elements in this group is there. So, these groups is called is a trivially groups. H is equal to E of a group G is called is a trivial subgroups. So, a subgroup H is a proper subset of a G is called a proper subgroup. If we have a H is equal to is a proper subset of a set G, then this H satisfies the properties of a group, and if it is a subgroup, so we can say that this H is a proper subgroup of the group G is there. So, in many of the examples that we have investigated up to this point, there exist other subgroups beside the trivial and improper subgroups are there. So, for example, you have to just say is this is H is this thing, and we have a one is identity, and H is a trivial is a subgroup of this. This is a subset of this, so this is a non-trivial. This is a proper subset of this. So H, this is a proper, this H is a clearly is a proper subset of this G. So H is a proper subgroup of this thing. So let us try set of we have to example set of positive real number under multiplication is not a subgroup of set of real number under addition, and clearly this set of all positive real number under multiplication are group, and also R under addition is also is a group. But you see we have to just say that is if we take a binary operation is multiplication, here we take a binary operation is addition. So clearly we have to take a two different binary operations. So this is a clearly R positive is a subset of R, but we can say that the binary operations are different. So we can say that this R positive under multiplication is not a subgroup of R under binary operation addition, since the binary operations are different in this case. So let us this is example we take U8 is clearly is under multiplication modulo 8. This is a form a group. Now we take a one subset of this H is equal to 1 into 5. So we have to by the Cayley tables we have to multiplication modulo 8. We have a 1 5 1 5. We have again 1. So this is clearly say that identity elements is here. So this satisfies all the elements of this table are the elements of this H. So clearly this can say that H is a subgroup of a U8 is there. So identity element is a 1, and we have to just say that inverse of a 1 is equal to 1, and in 5 is the inverse of itself. So this is a clearly this is a subgroup, and this subgroup has a every element x, then inverse of this is itself. 5 is inverse of a 5, 1 is inverse of a 1. So we can say that this is clearly H is a subgroup of a U8. Another example we have to take, we have to prove that GLNR be our user group of all invertible matrices under the matrix multiplication. We take a subset of this where a special case determinant of A is equal to 1. You know that the GLNR we have to just take GLNR is a set A belongs to the this is set, and then we have a condition is important we have to imposing the condition determinant of A should be not equal to 0. So this is the case we have determinant all the matrix is determinant of not equal to 0, or we can say that is a invertible matrices of n by n matrices. This is clearly this form a group under the multiplications. So we take a clearly this we have to just say that SL and R is clearly the subset of a GLNR. Now we have to just check this is this SLNR is a subgroup of a no of GLNR or not. So we have a condition is this determinant of A is equal to 1 is there. So to see it is close, we recall the property of a determinant. We say that determinant of AB is equal to determinant of A and determinant of a B. So if A and B are the element of a SL and R, then clearly we have to just say that determinant of A is equal to 1 and determinant of a B is also is equal to 1. So by this property of determinant of AB is equal to determinant of A and determinant of a B, we can say that determinant of A is equal to 1, determinant of a B is equal to 1, because A and B are the element of SL and R, and this determinant of a AB is also equal to 1. So if determinant of AB is also equal to 1, that means this AB should be the element of a clearly is the element of a SL and R. So this is clearly is closed under the operation of multiplication of these matrices. Now we have to this is clearly under multiplications is associative matrix. So there is no need of we have to verify in this, and we have a clearly if we have identity matrix, you know that the determinant of a any identity matrix n by n we have is equal to 1. So determinant of identity matrix is always is equal to 1. So identity matrix is only a determinant. So so this means identity is present there. If we have any identity element, we have to multiply a, we have to getting a, and then again we have a into identity. So the identity matrix is working as a identity elements of this. Now we have to find the whatever the inverse of a. So if a is the element of a is the element of S, L and R, and we know that the determinant of A is equal to 1. So determinant of A inverse can be written in the form of 1 upon determinant of A, and then determinant of A, if A is belong to the S, L, R, so determinant of A in this case is equal to 1. So if determinant of A is equal to 1, so we say that this is equal to 1. So determinant of A inverse also is equal to 1. So if determinant of A is inverse also is equal to 1, that means we can say that this A inverse is the element of S, L and R. So under the matrix multiplications, this S, L and R satisfy under form the group. So and this is a clearly subset. So we can say that S, L and R is a subgroup of a G and R, and no, we already explained you this S, L and R is called a special linear group in the when we discussing the properties of a and examples of a group is there. So next example we have two very interesting example. We take a Z4. You know that the element of a Z4 equivalent classes, but I have to write without the square brackets. So we have a 0, 1, 2, 3, and this is clearly under addition modulo form. This is a group. We can just take a, if you want, you can just say that we have to write a complete table 0, 1, 2, 3, 0, 1, 2, 3. We have 0, 1, 2, 3. Then you have a 2, 3, 0. 3, 0, 1, 0, 1, 2, and clearly this is a, we know that this is a clearly is a group under the addition modulo 4. Now we take S is a subset of this, so we have to just check under addition modulo. This has 0 and 2, 0 and 2, 0, 2. We have a 2 and 2 is equal to 0. So again this is closed, and identity element 0 is the additive identity under addition modulo 4 is here. So this is satisfy this. So this is clearly S 0, 2 under the addition modulo form is a subgroup. So this is clearly we can say that this S is a subgroup of Z4. So but we can say that in fact I just say that this it is the only proper subgroup of a disk. So we have to try to elaborate this case. We say that this S is the only proper subgroup of this set. When we say that there is a clearly we have the asking the subgroups of the Z4. So one of the subgroup is a Z4 itself, and another is a we have an identity element. So there is a two are the trivial subgroups of this set, and then after we say that it is a proper subgroup. So we say that this S is equal to 0 and 2 is the only proper subgroup of this. Let us see if we have to suppose S under function is a group, because I just already explained you by the table. This has a satisfy this is closed and contain inverse of 0 is a inverse of a 0 and in 2 is a inverse of itself. So now we have to just set if there is a possible there is any other proper subgroup is exists there. Suppose H we have to take any another subset is any other subgroup of this and one is the is in. So we take a H as a subset of this set and one is in H is there. So one is the member of this set H because 0, 0, 2 we have to taking. We take a suppose one is the element of a belongs to the this subgroup H. So if one is in H, then we have to just say that 1 plus 1 is because by the closure property. So 1 plus 1 is equal to 2. So 2 is also there. If 1 plus 1 plus 2 is equal to 3 is also there and 0. So this means in this case by the closure property, because we can say that 1 is the element of H, then 1 plus under addition modulo 1 is also belongs to the H. That means 2 is the member of H. And then we can say that if 2 is the member of H, then 1 addition modulo 4 1 plus addition modulo 4 1 is equal to, if this is also the member of H by the closure property. If this H under addition is a subgroup is a closed, so this means we can say 3 is also the element of H, and then we have to 0 is identity element is also there. So in ultimately if 1 is the member of this subgroup H, so we can say that this is H is nothing but is equal to you have a whole Z4. So if H is a, we have to assuming this H is a subgroup and this subgroup is containing one is the member of this H, then we have to show by the closure property this H is nothing but is equal to is a complete is a Z4. Let us try suppose another property is this. Similarly, if 3 we have to taking is in H, if 3 is in the H, those if 3 is the member of this subgroup H, if 3 is H, then under addition modulo 3 is also the element of H by the closure property. And if this is the by the closure property 3 belongs to the H, then we have to just say that we have to 2 is the element of H, and similarly we have to just say that 3 addition modulo 4, 3 addition modulo 4, 3 is also the member of H. Then we have to just say that 1 is the member of H, and then we have 3 is the member of H, 2 is the member of H, 1 is the member of H, and then we have identity is also the member of H. So again we have to getting H is nothing but is equal to Z4. So we simply say that H is not a proper subgroup. So this means only proper subgroup of, in this case we have a S is equal to 0 and 2. This is the only proper subgroup of this Z4 under the addition modulo 4 is there. So the only subgroups of this are, we have to just say that trivially subgroup. This is 0 is the trivial subgroup and Z4 is also the trivial subgroup, and this only proper subgroup is this S is a 2 0 and 2 is the member of this thing. So we have to just say that is this very clearly into this form. So we have to, up to now we have to just check that we have to checking all the properties of a group to show that if H is a subgroup or for a given group is any subset of this group set G is a subgroup or not. So we need not verify all the properties defining a group to show that the subset closed under binary operation is a subgroup. In fact, closure under binary operation and the existence of inverse are sufficient. Because we can say that clearly, because if we have to this is a set is equal to G, and G is already is a group under the certain binary operation, we have to checking the sub H is there. So this H is there. So we have to just check if we have a we just check if we take any two elements of this, because G is a closed, but we have to verify this any two elements this, and then we have to take an operation of this. Suppose this is A, this is B, then we have to show that A composition B is also the member of this set H is there. So and also we have to, because the inverse of every element is a unique in this set. So when we were choosing this set, this A is belongs to this set, then because A is also in G, so inverse of this element is a unique. So in this case we have to verify that the inverse of this A is also must be belong to the this same set is equal to H is there. So that's why we can say that no need of we have to verify all the properties of a definition of a group to show that a subset is a subgroup. Then it is enough to we have to show that there is a closed under the binary operation and the existence of inverse are sufficient to show that the any subgroup, any subset is a subgroup of G. So first we need to deal with the technical problem. When H is a subgroup of a G, then S must have identity and inverse for each of its elements. Are these the same identity and inverse for those in G? So that is a very technical problem, because in identity element for whole the set G is equal to unique. So this identity element must be the part of a H also, this is the same. So H has the identity and inverse of each element. If A is the element of a H and also the G, the inverse of this element is the uniqueness. So are these the same identity and inverse for those in G? So whatever H have identity and inverse for each of its elements, we have to prove that this identity this belongs to the same set is there. So I just prove this result, that let G be a group and H is a subgroup of a G under the certain binary operation. Then the identity element of a G and H are the same, or also we have to say that the inverse of a H belongs to H is the inverse of a H belongs to G. If H inverse of a H element of H is the H and inverse of H belongs to G are the same, because we have to taking the subset of this. So let us try to prove this result. Let EH denote the identity of H and EG denote the identity of G, and H be any element of H, and then clearly H is containing into G is there. This is clearly we have to into this form. So if EH I denote the identity of this element of H and EG denote the identity of this G, so H into EH is equal to H and E is equal to H by the property or by the definition of a identity element. And because H is the element of H, so H is also the element of a G, so we can say that similarly this because EG is the identity element, so H of EG is equal to H and EG is equal to H is there. So clearly we can say that because H is the element of H, the subset of a G, so this H is also the element of a G. If H is also the element of a G and EG is the identity element, so by the definition of identity again we say that HEG is equal to H is equal to EG H is it. So now HEH is equal to H and HEG is equal to H, so we can say simply is this equal to HEG is equal to this. So we can simply say that HEG is equal to H of EH. Now because this is a subset of this and then the group under this binary operation is a group, so all the groups of properties are hold here, and we can use the cancellation property. So by the cancellation property we can say that this is EH is equal to EG is there. So we have to prove that then the identity element of a H is the same as the identity element of a G is there. So we have to choosing two different identities, one is H and one is G, and then ultimately we have to show that these are to the same. Then EH is equal to E of G. So we have to complete the A part of the this result, that means identity of subgroup H and the same as a group identity of the group of G. Now next we have to try the inverse case. Let H is the element of H and H1 denote the inverse of H. So H1, if H is the, so we have to denote it, H1 is the inverse of H in H, and H inverse we have to denote H inverse denote the inverse of H in G. So if H is the element of this, then we have to say that H1 is the inverse of H in D. So this means this is given H in H1 inverse is equal to identity, H1 inverse H is equal to this. Sorry, this okay. This is H1 is the this thing. We just simply write into this. Oh, sorry. I just write in this way. We have to writing in this way because H1 denote the inverse of H. So H1 is equal to, we have a identity is equal to, we have a H1 and H. And H inverse denote the inverse of H in G. So this is EH, and we can say that H and H inverse is again identity of a G. H we have a inverse and H is the form. So we can just simply write this form. H1 can be written in the form of a, because we have write H1 can be written as a H1 into identity. Then we have to just say that H inverse is also identity. So we have to write in the form identity. So H inverse. Now we use the associativity condition H inverse H1 H into inverse. And now we have to just check this H1 H is also identity. This is, and we have a, so again this quantities you have to just check is identity element. So this is equal to H inverse. So we check H1 denote the inverse of H in H, and H inverse denote the inverse of H in G, but we have to show that the H1 and H inverse are the same. So inverse of H belongs to H and the inverse of H belongs to G are the same. So this means any element of this, we have to inverse of this element in the same is there. Okay, so by this we can say that clearly, if we have to just say that if we take any set G and we have to taking any subset of this H, though we have to show that if identity element must be belongs to the same as the same that belongs to this H, and also we have to show that if inverse of this A, this should belong to the inverse of A. That is a every element has a unique inverse in this case. So let us now we have to certain criteria for determining exactly when a subset of a group is a subgroup. So let us examine some criteria. So for determining exactly when a subset of a group is a subgroup. So let H be a subset H of a group G is a subgroup of G if and only if these three conditions are hold. First one is H is non-empty, then we have to show that this H is closed, and also we show that H inverse is also belongs to the H. So we have to prove this theorem by if any subset H of a group G is a subgroup. So this is a two-way. If we have to just check this one way, if H is a subgroup, then if H is a subgroup, you have to just say that if H is a subgroup of a G, one condition. So if H is a subgroup of a G, then clearly E is the element of a H. If E is the element of H, because subgroup is identity is the element of H. So if E is the element of H, this means H clearly is a non-empty. At least identity elements belong to the this set if it is a subgroup is there. So first condition is hold in this case, and also H is a subgroup is there. So if H1 and we have to take a H2 is the element of H, because H is a subgroup. So H is a subgroup means H is a closed under the binary operation. So H1, H2 is also the member of a H is there. So clearly we have to just say that by the second property is hold by the condition is there. So we have to just take a third one is also because H is a subgroup. So if H is the element of H, so if H is the element of H, then every element has an inverse. So then H inverse is also belongs to the H. So because H is a subgroup, this means H satisfy all the properties of a group is closed, associative, existence of identity, existence of a inverse. So then we have to prove. That means one way, if H is a subgroup of a G, then these three condition is hold by the definition of a subgroups and groups, we can just say. Now conversely part is interesting. We have a assuming that all these three condition A, B, C satisfied, if H is a satisfies these conditions, then clearly H is a closed by the condition of a second, and if is closed by the condition of a second, clearly H1 H2 we have to just say that. Now second, if H is a, since H is a non-empty, then there exists at least one X belongs to H. If one belongs to X belongs to the H, then if C implying by the C, X inverse is also belongs to the H. If X is the element of H, X inverse also is the element of H, then by the condition B is saying that the closeness, so this means E can be written as X inverse, so X inverse is also belongs to the H. By the second condition, he said that is H is the element of H1 H2 is the element of H. He is saying that H1 H2 is also the element of H. So if X is the element of H, then inverse of this element by the condition C, X inverse is also the element of H, and this E can be written as a X inverse is identity. So this X inverse is the element of H. So this means we can say that E is the element of H. So H contains the identity element. So clearly H contains the identity element. For any H belongs to H, it inverse in G also. So we have already proved that whatever the inverse of H belongs to H is also the inverse of H in G. So H is the element, it is inverse in G also serve as the inverse of H, and due to C is there. So we show that every element is satisfy this all the three. So as H inherent the associative property from G, so it's form a subgroup under the binary operation of this case. Let us try one example, and then we have to move further. We know that Z8 under addition modulo 4 form an abelian group under the modulo 8. So this is clearly under addition modulo 4 is a group. We take a subset of H is equal to in this form, and then we have to draw a table of this H under the addition modulo 8, and this table is like this. We have to just say that 0, this thing, and then all the elements of this table are the elements of H, then clearly H is a closed, and we can say that the identity of a 0 is equal to 0, identity inverse of a 2 is equal to, you have a 6, inverse of a 4 is equal to 4, inverse of a 6 is equal to 2. So every element has an inverse, and this is also closed, and also we have to just say that it's a non-empty. So this is clearly by the theorem is saying that if H is a non-empty, H is a closed under the binary operation, and if H is the element of this any element, H is the element of H, then H inverse is also the element of H, then this three condition is satisfying by this theorem. So since the subset H is a non-empty, and it is evident by this Cayley table that H is a closed and contains the inverse of each of its elements, hence H is a clearly H is a non-trivial abelian subgroup of this Z8 under the addition modulo 8. So by using this theorem, we can easily we have to no need of a checking all the properties of a group. We have to just take if H is a non-empty and it is a closed and also inverse is there, then we can say that H is a clearly H is a this subset H is a subgroup of the group G under the same binary operation. So I think I just have to stop here this lecture, and next lecture we have to continue. Can we reduce this criteria for more? In place of we have to this 3, we have to just combine these two because is the closeness and inverse is there. So by combining these two properties, we can say that we can say that if we have to only we have to prove that if H is a non-empty and any X is the element of this and X inverse are the element of this, then X inverse is also belong to the H, and then we have to show that this H is a subgroup of a group G under the same binary operation. So thank you for today's, and we have to continue in the next lecture, sir, other properties of this subgroup and criteria how to say into the subgroup.